I'm going to take the hint from yesterday. We got some feedback that you guys really would like to get through to some of the harder mixtures. So I've set myself that goal. The risk is I go a little fast and do some damage to your minds, and I really would appreciate it if you just broke through whatever that little American barrier is that you don't talk in these classes and just stopped me somehow. That wouldn't offend a colonial like myself. So if I must start with this little psychological experiment for you. We have a child abuse case, and a psychologist testifies, and he says this child rocks, and 60% of abused children rock. And I would ask you, what is your interpretation of that evidence? Say it again? Yeah, that sort of thing, yeah. I don't know if you're all this sitting, how you'd interpret that, or you just don't want to answer, or... Now, so thank you. Was everyone sitting there with that thought in their mind, but too terrified to actually ask or something? I come from a country where if you think the speaker is speaking nonsense, you stand up and yell balls. So just go for it, guys. So you really need to know something else, and I'm so grateful you said that. So if I told you 1% of non-abused children rock, okay, 60% of abused children rock, 1% of non-abused children rock, this child rocks. It's sort of, what do you think? Say it. It's really hard to hear actually up here.
That the fact that you know that it broke, that it rocks, still doesn't tell you anything.
Okay. How about if 60% of non-abused children rock? I agree that clearly doesn't tell you anything, because exactly the same fraction of abused children rock as non-abused. But if 60% of abused children rock and 1% of non-abused children rock, then rocking is more common amongst abused than non-abused, right? We can agree that? Right, does that tell us anything about whether this child is abused? Well, it actually does. Now, I see some head shaking. Now, look, you guys do DNA, right? So the suspect matches, and let's make it 1% of innocent people match, right? You guys, it's 1 in a trillion, right? But let's do 1%. Do you think that means nothing? This is amazing to me. No, it's not amazing, actually. This happens everywhere in the world that I put this example up there. The evidence is actually 60 times more likely if the child is abused. Right, if I use that 60 to 1. Is that a fair statement? The evidence is 60 times more likely if the child is abused. Right, I just want to crank back. I wasn't going to crank back, but you've made me. Oh, I swear I have Bayes' theorem in here somewhere. And that's because I've hidden it, because Chris McGuire took over my slides. Let me see if I can just find Bayes' theorem. Because my suspicion is that you've seen this, and I think I can't project it, but... Okay, can you see that evidence given HP there? Okay, let's make HP the child is abused, and HD the child is not abused, and E the evidence, the rocks. Okay, can we see probability of evidence given HP over the probability of evidence given HD? Can we see that's 60? Okay, that's the likelihood ratio. The likelihood ratio is 60. The prior odds are the odds the child was abused before you heard this rocking evidence. So I don't know what that is. It's, some witnesses have come or something, right? But the evidence has a factor of 60. We've improved from wherever we were at first, whatever all that prior had done, to the posterior. And can you see those other ones? HP given E. That's the probability he was abused given the rocking. And that's the way around we want it, all right? I'm going to give you that little 60. Let me just turn it into, sort of the way we're used to, right? We're going to give you that 60. And that's all I'm going to do all day, is I'm going to calculate those little things. Now, you guys who use RMNE and other things, you think you haven't got prior rods. You have. They're dressed up in there as well. You're doing something similar. So we're giving you that likelihood ratio. It says wherever you were beforehand, you want to go up by a factor of 60. I don't know if that worked. I used to teach in England. I went to England and I was a colonial lad from New Zealand, so they put me in the shed out the back. And I was going to tea and I was sitting down with Peter Gill and these people who were inventing DNA. And they said, how would you do this problem? I said, oh, it's easy, it's like this. And I sat down at tea the next day and they said, how would you do that? And I said, oh, it's easy, it's like this. And they said, oh, you better come and work on DNA. And I got moved from the outbuilding into the main building inside. I thought, wow. And the man came in and he put up a 2 clothes peg. And I said, well, what's going on? He said, you've been promoted, you get 2 clothes pegs. I said, oh gosh. He said, if you get promoted again, you get 4. And if you get promoted to the top, you get 6. Okay. And I was sitting there and a man came in and took away my white blotting paper that you write on. I said, oh, what are you doing? I sort of used that. He said, oh, you've been promoted, you get green. And if you get promoted again, you're going to get blue, right? So they elevated me eventually to the training unit in the UK. Now, in the UK, I was very impressed with the training. You'll go away to this little country pub and you have to hand in your cell phones. And we used to do 1 week's training on DNA analysis just on maths refresher, right? And then you go back and work for a while. And then we'd give you 1 week's training on setting hypotheses and working with that formula. Then you go back. You come back and we'd train you to do single source stains, right? And you go back and work for a couple of years. You get promoted to mixtures. Give you another 2 weeks training for mixtures, right? I hope one of you in your head's adding up what this has come to, right? And then you'd go back, and then finally, when you'd reached the final level of elevation, we'd train you on low template DNA, right? And that was the end of your life. You never, after that, got a nice case again. Everything you ever had was, but just the professionalism of that training. So I'm not too surprised that when I just played with that little formula for you, or even gave you what I thought was relatively routine evidence, that rockin' one, that's actually, that kind of evidence gets given every day. All right, so what are the lessons? You cannot interpret evidence with one hypothesis. Now, you yelled that at me, right? I gave you just 60% of abused children rock. You, one of you, and I hope the rest were thinking it, thought, I need the other probability, the probability under the alternate, right? And it's the ratio of those two. You need 2 hypotheses and 2 probabilities, and it's the ratio of those that matters. If that's the only thing I can teach you today, then that's cool. I'm hoping I can do a little better. Models to interpret, oh hell, I promised I would use that for 34 cycles and I didn't. This is LT-DNA, right, any low template. I'm going to use a very poor nomenclature. I'm using it deliberately because if I use proper nomenclature, the equations just get so ugly that nothing will happen. So I'm going to have these terms. I'm going to have drop-in. Now, I saw Mike Coble mention drop-in to you yesterday, and I did not feel a recognition in the audience. So this could be for 2 reasons. You've never heard of it, or you don't have it. So I'll just talk it through. Drop-in, we have a model of alleles snowing from the ceiling, just single alleles snowing from the ceiling, and they pop into your Eppendorf tubes, all right? And it's called the allele snowing from the ceiling model. And at 34 cycles, you can amplify a single allele, and we see essentially random peaks in our negative, and these are very worrying. We have an ultra clean facility, all the UV lights come on at night, and the air only comes in and through a filter, and every door is positive pressure, so you open the door and the air comes out and these sort of things. It's as clean as we can get, but we get this drop in, and we think it's snowing from the ceiling, or it's little fragments stuck on the glassware or the consumables, right? And you remember we had the German phantom problem? German phantom, heard of the German phantom? Wouldn't mind hearing of the German phantom? All right, so we had 3 hits on the database in the UK to each other, and no perpetrator. Couldn't find anyone, and a major investigation was begun. And after a really long bit of work, it was tracked to a worker in a plastics factory in Germany, and it had snuck in on the consumables. So we've cranked up the sensitivity so high now, we just get these little random bits, right? That's drop-in. Now, if you don't have drop-in, you can just forget that term. We call it C. It used to stand for contamination, but we've renamed it drop-in because we felt that was more polite. C with a little bar on top of it means not drop-in, okay? Drop out, okay, I've got D and then D bar, and I've been festering in my head about what to do about a homozygote. Is it harder to drop out a hom than a het? I think it probably is. So we've got that D with a subscript 2, and the little 2's just to help you think that was a hom, all right? You know, 2 alleles, right? And a bar on top of it. That's my nomenclature. It's pretty ugly. I'm going to estimate some LRs, and I can do it for any number of replicates. And if any of you are interested, this is the basis of the 2 systems that I believe we'll be choosing between at some future time. So true allele does the same thing. All right, so we have 2 replicates, and I've cunningly named them R1 and R2. And I'm going to imagine R1 as A and R2 as AB. And I need to calculate that little ratio I was talking about, the probability of that evidence if the profile is from the suspect, and the probability of the evidence if it is from someone else. Now I'm just going to drop my proof up here. I don't expect you to reprove this as I go, but I don't know, I feel the need to put it up here. But it teaches much better in an example. So I'm going to teach it by an example. I'm also going to do a little bit of cheating. I don't want to go into population genetic models. I mean, we're here for mixtures, and you guys tend to use recommendation 4.1 from NRC2. I don't. I use a different model, and if any of you are old enough to have used the product rule, we all used to use that, right? I just don't want to go there. I'm happy to go there on a different course, but I'm going to cheat. So P of AB is the probability of AB, and I stick the 2 in front of it because that's a het, all right? So AB is an ordered set of alleles, and I have that given sign AB at the back, and that allows me to use different population genetic models. So I'm just going to cheat and not go into the model. If you guys leapt up and said, gosh, this looks like good stuff, I want to implement it, we would insert recommendation 4.1 in here. And in fact, Todd Bill, who has absented himself, I notice, has been working on his RMP system. And again, we've written it in a generic way, and we can insert the 4.1 into his system. All right. So it actually helps me to start with 1 replicate, AB given AB, and we need to think about what the true offender might be. So remember, the sample is AB. What could the true offender be? If you accept that things can drop out and other things can drop in, right? If you can drop out and you can drop in, then you can actually explain anything, okay? Now, if I was a computer, which I'm not, I would enumerate everything, but I'm not. So I'm going to try and be sensible. I'm going to stick it to AB, AA, and BB. Right? Just cruise with me a while. This probably looks pretty weird. So possible offenders are an AB. How do I get an AB profile from an AB donor? I've got time. Okay, I don't drop out the A, I don't drop out the B, and I don't drop anything in. Okay, could I write that as a D with a bar on top of it, a D with a bar on top of it, and a C with a bar on top of it? I saw a few people sort of giving me nods of approval, right? Is that, if I'm stuck here, the rest is going to get worse, so don't let me go by you here. All right, how do I get an AB from an AA? I heard a lot of noise, and that, that was so positive for me. I didn't hear actually any of it, but at least you said something, right? So I don't drop out the homozygote, right? That leaves me in A peak. I've got to get the B in there, so I have a little allele snow from the ceiling with probability C, and we hope C is a really small number, right? And it has to be of type B, so I've got you guys would call that the frequency of B, but I like to call it the probability of B. All right, how do I get an AB from a BB? I don't drop out the B, I have a snow, and it's type A. All right, you got the gist of this? The entire world is going to open into a beautiful vista of understanding and ability if we can get through this. Right, that maths I showed you, my proof says multiply across and add down. Now maybe you can go back and just check one day that is true, right? Multiply across and add down. And yes, please. Okay, so C is the probability of an allele snow happening, and we hope that's some number like 1 in 10,000. The bar means of it not happening. So there's 1 minus that, so 999 out of, or whatever it is, out of 1,000. Okay, it's 1 minus. You've put your finger on my bad nomenclature, and that's a fair cop, right? The bar means not. It's a statistical term for not. You just put a bar above a thing. All right. If HP is true, then the real donor is an AB. If R1 is really from the suspect, how is the evidence explained? Well, we've just done it, right? We did it in our little warm-up. No drop in of an A, no drop in of a B, no drop out of an A, no drop out of a B, no drop in. So it's that. This has caused so much trouble. No one's stood up and yelled at me yet, but maybe you will, all right? There's the formula, and boy, that looks pretty, doesn't it? If you assume C is low, now you guys didn't seem to react too badly to C. We're keeping it, at 34 cycles, we're keeping it to about 1 locus in 1,000 has a drop-in event. At 28 cycles, we don't have it. So if you guys are working at 28, you probably don't have it and probably aren't worrying about it. Those of you who are doing the Y chromosome, you know, you're probably working at 30 or 32, and I bet you do have it. Pretty low rates, but you do have it. Anyhow, if you set C to 0 in there, right, if C is 0, then C bar is 1. Okay, and 0 times anything is 0. And can you just see just this most beautiful destruction of that equation when you do that? Yes, please.
So if we're going to give C bar as a number at some point, why would we include it for the scenario where you have maybe suspect and the evidence is AB? Because you could have drop in, but it would just be maps.
You know, I'm not very sure I understood that. Probably because my hearing's a bit rubbish, but I would advise that if we computerize this, we don't set C to 0, we set it to a number. Yes, you could have drop in and it's masked. You mean we could have dropped in a B? Is that what you mean? Yeah, sure. So if I computerize this, I just add terms endlessly, right? So I have a drop in and it's type B and I don't see it, right? So that's perfectly trivial in a computer and completely impossible by hand. So if you just allow me a little bit of liberty, when we program this, we allow this myriad of possibilities, most of which are ridiculous, all right? So, you know, how could I get an AB from an AB? Well, I could drop out the A, I could drop out the B, then I could drop in an A and drop in a B, right? So I could, right? So, and the computer will do that, and it'll have a probability of tiddly, tiddly, tiddly. And, but in the human world, can you just give me some liberty for a while? Okay, so if we assume C is low, we get 1 over 2 PAPB, which is, if we're product ruling, that's 1 over 2 PQ. And that's what you guys have done all your life, right? You saw an AB, suspect was AB, you did it. And that turns out to be completely true and viable if your drop-in rate is 0. If your drop-in rate is 0 and you see an AB, then it's from an AB, right? Now that was all fun and it taught you it. Now yesterday I started talking about a non-concordance. So a non-concordance is where the suspect has an allele that's not visible in the profile. And these are the ones that are stressing our current systems. I hope you agree, they're stressing RMNE and they're stressing LRs. And I just want to talk to you about that and what the options are. I'll just pontificate for a small minute where we've fiddled around with the words non-concordance. So they've been called other things like dropped alleles, right? It's only a dropped allele if the suspect really is the donor. So dropped alleles shows a prejudice in our mind. The other one, a judicial one, was to call it a void, right? It's only a void if the suspect is the donor, right? So that's a bias in the judicial mind. So anyhow, let's imagine we have a low-level profile, AF. Now, I understand you call it X in America. Is that right? F in the UK. So F stood for failed. I don't know what X stands for. X is actually better because if you're doing calling alleles A, B, C, D, you actually get down to F pretty quickly, so we end up using F twice, which is a pain. But anyhow, I define F as any allele, and we're playing with this thing called Q, which is any allele other than those denominated. So just before I go on, AF, right? That's A and anything, and the anything could be A, right? AQ is A and anything, but the Q can't be A. Okay, just to get that into your head. Suspect is AB, so we have a non-concordance. Okay, how do you get an AF? Well, again, I'm going to be a tad pragmatic and say it's from an AQ, an AB, or an AA. I mean, you can make a few more and so on, right? Just going to do exactly what we did last time. How do you get an A from an AA? You don't drop out the A and you don't drop in anything. How do you get an A from an AB? You don't drop out the A, you do drop out the B, and you don't drop anything in. How do you get it from an AQ? Don't drop out the A, do drop out the Q, don't drop in anything. All right, you getting the gist of this? Multiply across, add down, all right? Suspect really is AB. How do you get it? Don't drop out the A, do drop out the B, don't drop in. A little bit of algebra that always makes you feel warm in your heart. And I like to fiddle that. So, typical behaviour of that equation. Now, what I'm going to pretend is that the blue line is correct. It's certainly, at this point of the modelling I've taught you, it's the most correct we can do. The blue line is the correct likelihood ratio. Ignoring the locus is the dotted line, and I believe that it would be a very common practice in the US. Is that true? A non-concordant locus would be ignored? I don't know. I don't know what your practice is. I did used to live here, so I should know a little bit. The 2p rule would be up there, and obviously I've invented some frequencies and so on to get this. Okay, and across the bottom we have D, which is the probability of dropout. So what do we notice? The 2p rule is never conservative. I wrote a paper a while ago called "Is the 2p rule always conservative?" And I know I've probably been the most controversial speaker you've seen today, and possibly for a very long time. I'm actually sort of very mild-mannered. I don't like to rock the boat. I do believe in our science. I do actually genuinely believe in DNA, so I'm not here to wreck the place, you know. So I wrote this thing, is it always conservative? And of course, I was trying to make this point. I referee for certain papers, and I saw this one that had taken it up, and it's actually entitled, "The 2p rule is never conservative." So someone had thought I'd been a little bit too mild-mannered and sort of, you know, supermaned it up a bit. Okay, so the 2p rule is never conservative if you have a non-concordance. Ignoring the locus is typically conservative, right? The dotted line is below the blue line unless D is very, very small. Now, I'm going to try a little novel experiment here of writing on a whiteboard. I don't know what your chance of seeing that is. I wanted a throat mic, but we don't have one readily available. So I'm hoping that by sort of talking really loud you can hear me. Okay, if that's our stochastic threshold, when is D very, very small? Remember, we've got an A peak and no B, right? D is very, very small when the A peak is just under the stochastic threshold. Okay, is that fair comment? We think that D is essentially zero when we hit the stochastic threshold. So when we're just under it, the chance of dropout is very small. Right, that is the risk zone, right? If you're looking at this little blue line, can you see that tiny little risk zone down one end? That's the risk zone if you're a locus ignorer. If you're a 2P'er, your risk zone is much broader. If I've made that point, then we're really doing nicely, all right? So this is the whole thing, right? No one at this point, well, that's not true. None of our current methods at this point can handle non-concordances with absolute certainty. We cannot predict the behavior of our current methods in the incidence of a non-concordance. All right? There is no way I can patch up RMNE. There is no way I can patch up binary LRs that I can predict the behavior in the event of a non-concordance. I hope that is said with as much clarity as it can be said. Right. Now, the risk is minor, right? There are ways we can ameliorate it, and what we've been doing maybe for 10 years is workarounds and patch-ups, right? And just sort of trying to struggle along. We don't want to change. We're happy where we are. Can we patch it, you know? So I am actually going to show you some patches. However, we live in exciting times. I believe we're at the end of the binary era. I've told you yesterday I've been a very bad predictor. I predicted all sorts of amazing things. I remember standing in a pedestrian crossing, which I think you guys call a crosswalk, in North Carolina, and I was there with Professor Weir, and we were doing the O.J. Simpson case, and he said, should we just say it's him? Should we do away with the numbers? And I said, no, we shouldn't do that, Bruce, that's terrible. And so we submitted a 1-inch thick report with 100 pages of maths, and you all know what the verdict was. And so Bruce said, look, we really have to do away with this statistical stuff in DNA. I believe it will go. Well, it's not gone. It actually represents 80% of all the trouble in court, is the interpretation phase. All right. Okay, I hope I've said that right. A non-concordance is the thing pressuring the binary models, and I don't care whether, well, I do care, but it affects both RMNE and the LRs. What are our options? True allele or the drop model. I've actually just shown you a model that works, right? That blue line is within QE of the truth, in my belief. So we have two options. And I'm going to take you through the drop model. I believe a lot of you have seen Mark Perlin, a close friend and a man I deeply respect, presenting on true allele. Those will handle non-concordances, right? So we do have this option. I might talk a little later about where I think Europe and Australasia might be going, but if you just let me just go for a little bit further. So if the person of interest is AA and the stain is A, you have no real problems. That is not a non-concordance. If the person of interest is an AB and the stain is A, you have a non-concordance. The 2P rule is never conservative. However, the 2P rule is not too bad if D is not small. If you just remember that blue line, it was always below the 2P, but it's sort of, you know, it was in a bit, it was close if D was not small. Ignoring the locus is not always conservative, but is okay if D is not very small. Now, I'm trying not to crack too many eggs and cause a huge back litigation here. As I said, we had a 5,000 case back litigation in Melbourne, Australia, and it was pretty damaging. So where do we stand in 2010? Well, I wish I'd written 2011. Okay, the binary model is under stress if it's non-concordant. I'll tell you what, it's 2010. We're doing this course in March, and Deborah, God love her, said all the material has to be submitted on the 24th of December. Now, the 24th of December is Christmas Eve, all right? And a boatload of immigrants had sunk off Christmas Island, which is a detention centre the Australians use. And we were doing this huge DVI of all these immigrants on Christmas Island. And I wrote to Deborah and said, do you really need them on Christmas Eve? Yes. So here we have it, the wrong date, and I blame Deborah entirely. Okay, so we have the binary model, which is under stress if non-concordant. We have the D model and the continuous model. Continuous model, only current candidate is true allele. All right, can deal with non-concordances. Right, increasing complexity and elegance, increasing use of available evidence, and I believe increasing difficulty of implementation and explanation, and more particularly explanation. I'm quite concerned about how we are going to represent Monte Carlo Markov chain evidence in court. Not so concerned that I've given in. I'm working with Mark Perlin. My plan is that I learn to do a Monte Carlo Markov chain simulation of true allele by hand, and I think I'll be able to teach it. I've been thinking of a little game, so with the class. So with the Monte Carlo is a Monte Carlo method, and you either pass information uphill or down. So I can sort of see how I could set you guys out, and you could pass the information uphill or down, and the answer would pop out somewhere. So I'm thinking about whether I can teach that. I noticed you guys weren't great on games yesterday, so I don't know how that's going to go. I have this great breeding game, actually, that I must try sometime with you. Okay. So can we nurse the binary model along for a bit further? We are, right? And until the end of March, we're nursing it along, and then we're going to change. So all non-concordances are problematic, but some are more so than others. Meant to be an allusion to all animals are equal, I think, and some are more equal than others, or something like that. So all are problematic. So we imagine the person of interest is a 7-9. That one on the left is highly problematic. Now, why is that? It's because the 7 is huge and there's no 9, right? So the probability of dropout is minuscule, right? And if you think back to that graph, that's our risk zone. What about the one on the right? Now, I don't want Mike Coble to yell up and yell at me that I'm looking under the bar here, but the 7 is small and there is a 9-ish, right? I'm not going to say there's a 9, please don't yell at me, but somehow that peak there comforts me. Yeah, stand up and yell at Mike. It's acceptable to have a peep, is it? I don't know. In my inner heart, I feel that right-hand one, yes, please.
I have a question about that left-hand case. Is this working? Yeah. Why would we not, knowing that we're close to the stochastic threshold and the probability of a dropout is really low, why would we not simply say that's an elimination, instead of calculating some very small probability that the suspect could be included?
I believe that's a very fair question. I would be very interested to know what you do. Not you personally, you plural, do. I have absolute knowledge that there are some laboratories that would pass that. It is hard for us to state with absolute certainty that is an elimination because dropout is possible. Now, what I believe most of you would do would be re-amplify. All right? Is that true? Oh yeah, well let's imagine it's looking okay everywhere else. No, let's pretend you've got 12 others and they're not looking too bad. You'd pass it, wouldn't you? Or you'd re-amplify, would you? Re-amplify? Okay, so I think, yes, please, do that.
I'd probably re-amplify that one and try to get it above the stochastic threshold.
I believe you would, yep. I'm going to accuse you of replicate shopping in a minute, right? You're John, is that right?
Steve.
Steve, okay, just remember your name. Steve the replicate shopper.
I could put a scarlet R on my horse.
Let's hold those thoughts because those are really valuable thoughts, because I'm going to go in a minute to what to do when you have multiple replicates. Because, of course, we're accused of just picking the one that fits, you know. And, you know, it's a fair criticism, isn't it? So let's get there. I'm not that far off. I don't wear a watch, and I haven't set the timer, which is, you know, that's one of the dumbest things you can do when you're a lecturer, is how am I? 35 minutes. Can I label that as the worst scenario and this one as not a problem? All right. Now, hope a slide's going to come up that does that in a minute. Okay, victim 7-8, person of interest 9-10. Okay, here's the behaviour of it. Again, I'm not going to drag you through the maths. So, ignoring the locus is a likelihood ratio of 1. If you think back to that formula, posterior odds equals the likelihood ratio times the prior odds, right? What happens if I multiply the prior odds by 1? Nothing, right? So inconclusive is an LR of 1. So whenever we call a locus inconclusive, we're actually mathematically multiplying by 1. Okay, it turns out ignoring the locus is never safe, but it's not too bad if D is high. Now, why is that? If D is low, the chance of dropout is low, I expected to see the minor alleles. Dropout is low, I expected to see the minor alleles. They're not there, right? So that's mildly exclusionary evidence. Right, if D is high, I was expecting dropout, so I'm not too worried that I didn't see them. Okay. I think this is just news, right? Is this news? Yeah. Okay. Change the person of interest. Victim still 7-8, person of interest 8-9. So now I've only got one allele sort of, what's the right word, right, guys? I've only got one allele missing, because missing means I'm assuming, right? I've only got one allele dropped, right? I've only got one allele non-concordant. It was our best attempt at a neutral term. Okay. So just take you through a case, RV Garside and Bates. And the background of this particular incident is that I was lecturing in Belgium in French, and it always stresses me to have to lecture in French. And this case had occurred, and a courtroom battle had occurred between David Balding and Ian Evatt. Now, if you're of my vintage, you would know that these are two of the gods of our science, and they'd had a good old scrap in court. And everyone in the class I was teaching, which was in Europe, were highly aware of it and said, well, what about Garside and Bates? And I didn't know anything about it. They were able to write out the problem, and I was able to write out the maths. But when I got home, I contacted David Balding, who's an Australian expatriate, and you know, we've worked up the case and published it. So I'm just going to go through it with you. So what we've got is lots of victim DNA, 17 STR alleles at 10 loci. Minute traces of an offender. There are 8 alleles not masked by the victim allele or artifacts. The defendant has 11 alleles not masked, including all 8 of the minor components that were seen. What to do about the 3 missing alleles? So there's a trace peak in each position, not to reportable standards. I mean, that would probably rest my soul, to be honest. One's in a stutter position, and 2 are at high molecular weight, which is more susceptible to drop out. So here's the story. Richard Bates was convicted of the murder. His co-accused James Garside was also convicted of the murder and received the same sentence. The victim was Marilyn Garside, the estranged wife of James. It was the prosecutor's case that Garside had hired Bates to murder her. Marilyn Garside was stabbed and killed when she answered the front door of her elderly mother's house in Rose Lane, Romford. The prosecution alleged that Garside was the only person who knew that Marilyn would be visiting her mother at that time, and the mother's Mrs. Barbara Rawle, and that Marilyn Garside would answer the door because her mother walked with difficulty. So when calculating the probability match, now this is taken from the judicial review, these strange words. Each sample, Dr. Evatt, the expert statistician called on behalf of the prosecution, attributed a value of 1 to each of the voids, treating it as neutral. Okay, so now you know what all that was about, right? He put in a 1, right? On that basis, he calculated the probability match, that's the judicial words, to be 1 in 610,000. So I notice every other person has put up an eyesight test for you guys, and here's my one. And I've made it in sort of a pale blue as well, which doesn't help, but can we try to see this? So there's Richard Bates, and below is the sample on the chrome handle of the front door. And the little black lines show alleles that correspond. And the little yellow lines show alleles that correspond, but we wouldn't take too seriously. They're both in stutter positions and both small. And here are the 3, I'm going to use the word voids, but you know I prefer non-concordance, but they're on as like voids. So what do you reckon? See, I think you guys, well, some of you would just drop those loci, which is putting in a 1, right? And that's what Ian Evatt did. Some of you would re-amplify, but I'm going to tell you there was a lot of re-amplification attempt here, and this is the best of numerous efforts. So David Balding was pretty grumpy about this. Here's what he says. In my opinion, the prosecution had a potentially arguable case, but they did not make it. Now, he says that because when he and I worked up those loci, using the method I've shown you, the likelihood ratio drops, but not much, right? So that 610,000 drops, but, you know, it's okay. Had a potentially arguable case, but they did not make it. Missing alleles were treated as neutral without any analysis or reliance on established guidelines to justify this. I mean, if I was testifying in court and David Balding was saying things like this to me, I'd be trembling. I don't know if you've met David, he's mild-mannered, brilliant, you know. If he says this, he means this. The judge accepted evidence that missing alleles had been adequately discussed for jurors to make their own assessment. Well, do you honestly think jurors can do that probably of drop curve in their head? Okay. So you laughed, and I welcome that laughter, because in doing that, you accepted to yourself the responsibility of representing the evidence accurately. If you think that through, you laugh because you knew the jury couldn't do that. So if the jury can't do that, you have to. You have to represent that evidence accurately. All right? I disagree, says David, and regret the lost opportunity to apply pressure for an achievable, better standard of reporting. Okay, replicates. So person of interest 7-1, replicate 1 on the left, replicate 2 comes through, practice I've heard of, pick one. I saw some head shaking. I love head shaking at that point. Let's imagine you pick one. I'm aware of 2 practices. You pick the best one or you pick the worst one. That does sort of cover it actually, doesn't it? You know? So Melbourne in Australia, pick the worst one. So I asked them why they replicate, right? Because they've always got the worst one first, so they do another one to try and make it better, but they always, because they want to be conservative, pick the worst one, right? They want to be conservative, so they pick the worst one. I said, well, why'd you replicate? You're going to pick the worst one. Right, and if you pick the best one, you're being the opposite of conservative, aren't you? You're sort of picking the one you like. Consensus. Now, Mike Coble introduced this yesterday. He introduced it really nicely, so I think I'll give it a glib repeat. Composite, and I'll just define composite in a minute, but this is a behaviour that my own lab was doing without my knowledge, and it gave me the, it made me very concerned. There is no published support for composite. Now, it might actually be okay, and I'm trying to publish some support for it. A bit reluctantly, I looked at it and said, this is a bad practice, I need to look at it. And I worked through it, and under certain circumstances it can be justified. So I'll talk to you about that. But really the best one is to mathematically treat both. And I really want us to get out of having to pick one, pick a consensus or pick a composite, which are all summaries of the information. And every time you summarize information, you degrade it. All right? And the best way is to treat both. So if you treat both D-model or true allele. True allele's a piece of software, beautiful. The D-model, I've already taught you the essence of it, and could you see what I was doing there? So D-model, highly teachable. I could teach you to do two-person mixtures by hand on paper, or it goes into Excel. So a few people I've taught have made up Excel sheets that do it. And one of our colleagues, Todd and I, and I think Jack Ballantyne worked with this guy, Steve Myers. He's just an Excel whiz. So, we can put it into Excel. But the good thing about the D model is I believe you can see the steps of what it's doing. But I don't want to argue against true alleles, so, Okay, report the most informative. Accusation of bias. It's actually not that obvious which is the most informative. It's sort of a little bit of, most people say whichever one's showing the most alleles above the baseline. And would we change our view of which was the most informative depending on the person of interest? Because if we did, that would be a very naughty thing. And we would be accused of replicate shopping. I mean, what if the second one doesn't get the answer? Do you do a third? Okay, reporting the most conservative should be safe to accusation of prosecution bias. The most conservative does in fact depend on the person of interest. It is very wasteful of information. I would ask you why you'd replicate it at all. Coming to the value of consensus, this paper, in fact, this paper and its follow-up are both in FSI Gen and Press. And they're quite good. So they've introduced a nomenclature I wasn't familiar with. So let's talk about 2.2 and 2.3. So consensus means if you see a thing X, you say it exists. So let's talk about 2.2. If you see an allele twice out of two replicates, it exists, right? 2.2, X is 2, N is 2, right? 2.3, if I see it twice out of 3, it exists, right? So you get the gist of 2.2, 2.3. Now I'm a little disappointed in the material they published, but let's talk about drop-in. So we think alleles snow from the ceiling. So as long as the replicates are separate amplifications, a drop-in in one should not, replicate in the other. So here we are. So can you see the number of drop-in alleles there? And let's look at X equals 2, N equals 2. It keeps the number of drop-in alleles quite low. I'd actually suggest they're a bit high compared with some people, but this is their lab, right? So 2.2, seen it twice out of 2. 2.3, seen it twice out of 3. Now, if you come down to the bottom one, how many alleles, correct alleles, do you score? And what we do is we benchmark this against what you got at 28. This is at 34. So if you got 0 to 10 at 28 and you ask for 2 out of 3, you'll recover 57% of alleles. So hopefully that gives you the idea of what consensus is. And most of us are working right now at 2.2 or 2.3. So we would replicate and use consensus right now. Come the end of March, we're going to flip to the D model, which multiplies them both. All right, composite. Basically, if you see it once, you call it. It's okay if alleles are always alleles. So for allele to always be allele, your drop-in rate has to be 0, and you have to never have big stutters or over stutters. Right? You have to, every time you call an allele, it has to be an allele. That's fine. If you can guarantee that, then composite is right. So I think you have to have no drop-in, no forward stutter that you'd ever call, and no big back stutters that you'd call. And remember, you could easily be in a mixture. It's not, you're probably mentally visualizing a single source stain and forward stutter. No, get away from that, guys. I want to make your life horrible, right? So let's have a mixture with 2 alleles separated by 2 repeats, right? So we've got a backward stutter and a forward stutter. Would you call that as an allele, right? So I want to make your life hard in this, right? Your alleles always have to be alleles. And maybe a few other things. So the risk is not empirically assessed fully. It is in part. And we can theoretically assess it using that model I've done. And I've drafted a paper and I've got it through the referees. And the referees came back and said, look, this is all very interesting. You've written this up for single source, but that's really not very exciting. I really want to see the effect of composite for complex mixtures. So I think that's fair cop. I have to rewrite this now for 2 and 3 person mixtures. What will the effect of composite be? So I'm hoping composite isn't too common. It's frighteningly common in the Y chromosome work. And at this point, as far as I know, it has no published support. Okay, mathematically combining. Just so far the best. Why is it the best? All summaries of information degrade the information, so don't summarize. Replicate 1 is AB, replicate 2 is A, the person of interest is AB. This is stuff you are becoming familiar with, right? So what I've got is on the MJ side, a possible offender, AB. How do I get replicate 1, AB? No drop out of the A, no drop out of the B, no drop in. How do I get an A? No drop out of the A, drop out the B, no drop in. Okay, I'm just going to do lots of that. Multiply across and add down. All right. And I don't know what's going to happen next. So I've now imagined 2 different numerators. So the numerator depends on what the person of interest is. So the numerator if the person of interest is AB is that, and if it's AA is that. So I'm going to have 2 different likelihood ratios, and I hope I've plotted them, but I've just got this terrible fear I haven't. No, I'm okay, I have. So if the person of interest is AA, we've got a strange scenario, remember. I'm having to envisage a drop-in because one of those replicates was AB. Here's the shape of the likelihood ratio. And we see that ignoring the locus is not conservative for most of the behavior of this. And I was hoping I had the AB one. It's shaped the other way. I haven't drawn it, so I'm going to draw it for you mentally in your minds. Remember, one replicate is AB and the other is A. So looking at this, you'd probably put your heart on it being an AB, right, with the B having dropped out. Okay, The shape of the curve is the mirror of that other one, just goes up and across and down. And in fact, if your drop-in rate is 0, the likelihood ratio is 1 over 2pq, right, which is what you would use. I'm going to just write that up on this little board, having not drawn it. Oh, thank you. Thank you. This might be dexterity beyond my ability here. Replicate 1 is AB. Actually, why don't I swap those round? I'm going to be Steve, the replicate shopper here. Replicate 2 is A. Replicate 1 is A. He got that first. His person of interest was AB. So Steve, who I have every confidence is a diligent scientist, decided to do it again, and he got the AB next time. And here we are. What do we do? I mean, we've done a bit more analytical work. What do we do? Well, if you pick that one, the defence are going to say, well, come on, guys. And if you pick that one, I'll say, why'd you bother? So let's multiply them up using that little formula. And the shape of it is like this. There's the neutral line. That's ignoring the locus, and the LR is just up here. So for almost any drop probability, the likelihood ratio is a very positive thing. And that's relative to 1 over 2 PAB, which is probably what you'd use if you assumed this was indeed an AB, if you went with that one, right? And if the drop-in rate, if your drop-in rate is actually 0, that is actually completely true. I apologise for a slightly substandard presentation of that point. I may rework that if I get time. Okay, as a principle of probability, this is universally true. It's not just true in DNA, this is universally true. Ignoring information is conservative on average if HP is true, but not conservative if HD is true. I want to put that into pugnacious talk. Now remember, I try not to be pugnacious, but maybe you'd let me get away with this. Ignoring information benefits the guilty and hinders the innocent. That's what that says. You can think this through. Imagine you had a 15-plex and you just cut off the 15th. Didn't look at it, just cut it off. You would get a lower number, and that would benefit the guilty, but you would hinder that tiny fraction of innocent men who were excluded at that last one, right? Now, I mean, the massive power of DNA helps us because almost no one survives 14 and then gets excluded on the 15th, but, what if I gave you a duplex, just to make it hard for you, right? And made you cut off one, right? So you only look at one. It would lower the number, so that would help the guilty, but there would be a significant fraction of innocent men who would be excluded by that next one you're ignoring. So ignoring information is conservative on average if HP is true, but not conservative if HD is true. So I'm opposed to ignoring information. Now what we've all done is we've done little workarounds. We don't actually ignore that 15th locus, do we? We actually have a little peek, see, ooh, it's not an exclusion, so I'm safe to ignore it, right? So that ameliorates the problem a lot. We've got in place workarounds where have a little look, no, it's not an exclusion, but it doesn't make my standard, so okay, that ameliorates it a lot. It's not as bad as it sounds. So I'm on a number of committees. I sort of told you that one of my goals is to try and align SWGDAM and ISFG guidelines. This came about because of a court case I did in Sydney, Australia, and I was following the ISFG guidelines. And this probably doesn't happen in America, I don't know, but lawyers are very good at this. Every time I followed the ISFG and it was different from the SWGDAM, they said, why aren't you following this one? Have you had some of that? Look, if I was a lawyer, I almost wouldn't bother studying science. I'd just get the swig dam and the ISFG and find all the differences. And whichever one you followed, I'd tell you, why don't you follow the other one? And then I'd just read the list of names on those papers and say, well, all these people disagree with you. So I had a real hard time of it, actually. So I want to try and align them. The Atlantic doesn't need to be that wide. No, I don't think that'll happen in my lifetime, but I've got some very good friends who are trying to work with me, Jack and Mike and Todd. They're all agreed. Strangely, I'm having more trouble with the Europeans. But you know, give me my last 10 years, and then one of you young ones can take over. Now, down in Australasia, we have a thing called the stat swig, and we're having an alignment process. And we're aiming at standardisation. Now, there are two sort of goals you can have. You can have minimum standards or standardisation. They're quite different, right? Minimum standards, you accept diversity. Standardisation, you kill diversity. And we've been told to do this. The commissioners of police were sick of trouble in court and said, make a standard. I want the same case done in two different states to give the same answer. And you're all aware we got mocked a bit in New Scientist by Linda Geddes. She sent I think a North Carolina case out to a number of people in 19 different labs or something, got 26 different answers. And there were terrible headlines. I can't remember them, you know. Was it trial by chance or something, you know? There was some real catching headline I wish I could remember. And they're mocking us because we couldn't get the same answer twice. So that's what we're up to in Australasia. And I told you I'd probably confess that we're probably going to go with the D model. And I think I'll tell you why, right? First of all, I'm on the patent. But I've actually argued against it. But the people have voted for the D model over true allele because they feel they can understand it, right? I'm going to try and compensate for that by learning true allele to do by hand and teaching it with a game, right? But that's where StatSwig is going, and I think that's where ENSFI, the European network's going, if that's any information to you. So I believe we're changing. Well, we are definitely changing. How am I doing, Debbie? What time have I got left now? Okay, so I believe the future is the death of the binary model. I have been notoriously bad at predicting these things. So it is not inconceivable we're here in 10 years, I'll be in a Zimmer frame, and we'll be discussing the binary model. I've been wrong very often. I'm going to talk about possible ways of pushing out likelihood ratios and extending their lifetime for a little bit longer. I don't believe in it. I believe we should change, but I'm going to teach it. So, unconstrained combinatorial approach. Again, this is a thing that is, it's going to sound like gobbledygook in theory and be trivial when I actually give you some examples to do. This is teach by example. 2 days hands-on of this, you'd be old hands. So, two-person mixture, 4 alleles seen, HP, suspect 1 and suspect 2, HD 2 unknown individuals. I don't actually agree with this formulation. What do we get? We're going to need factorials. I'll just remind you, factorial is a positive integer n. So 5 factorial is 1 times 2 times 3 times 4 times 5. And I'm going to give you some factorials. So there's 1 factorial is 1, 2 factorial is 2. And can I ask you to note how quickly that blows up? So sort of, you know, I guess we could say it messes around a bit. But by the time we go 4, 5, 6 factorial, those numbers are really moving. Okay, and I'm going to need you to be able to do permutations. Now, you actually could do this at high school, but you probably might be a tad rusty on it. So there's the formula. It's in the notes you don't have printed, but it is in them, and I'll just teach you a little bit about how to do it. Actually, why don't I'll just have a small segue for a minute here, because Todd said yesterday, where did the 24, remember he had 24 turn up in his formula, and then he said, where does it come from, and he wrote it up. Okay, so let's do it the hideous way and the easy way, and that'll be my 10 minutes and you can have lunch. So I'm just going to try and turn this on and see if we're going. Yes, we are. Okay, let's do A, B, C, D, 4 alleles. How many combinations? So we've got A, B, C, D. How many combinations? So there's A, B, C, D, A, C, B, D, A, D, B, C, and the swaps, all right? So that's a het, so that gets a 2. That's a het, so that gets a 2. And when you swap, that gets a 2. All right? I realise that was a bit fast, but, 2, 2, 2, 2, 2, 2. 2 times 2 times 2 is 8. And 8 and 8 is 24. And that's what Todd wrote up. Now, just use this to show how this formula works. N is the number of alleles. So n factorial is 4 factorial. And then the m's are the counts of each category. So how many A's are there? 1. How many B's? 1. How many C's? 1. How many D's? 1. All right? 4 factorial is 24. All the ones are 1. That's 24. Right, that's the easy way to do these things. It's possibly lower understanding. I've given you a formula that can do anything, but you don't have to think like this. So I'll just test you guys. This is, can you do that one for me? A, B, C, C. You got bits of paper in front of you. I realise that in America we don't do class participation, but can you humour me? And you calculate that, and then I'll calculate that, and anyone who gets it right is allowed to go to lunch. Okay, you're not allowed to log, but I've put up my answer. If you obtain that answer, you can fold your notes and go to lunch. If you don't obtain that answer, can you make yourself known to me by some mechanism, because I'm going to need this.